Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And in this video, we are going to talk about some of the most important interview questions on principal component analysis, or PCA in short. Now, PCA is one of the most favorite topics for a lot of interviewers. And as a candidate who is applying for a data science role, you are expected to know a lot of the internal details about something as fundamental as PCA. So it's better to understand how do things work and some of the most important interview questions that are asked when it comes to PCA. So let's start with the first interview question, that is, what is PCA? So PCA is one of the most classic and oldest techniques for dimensionality reduction. There are other usage to PCA, not just dimensionality reduction, but primarily it is used for dimensionality reduction. And it's great for an initial start, but often has a few drawbacks. And these drawbacks were later addressed by techniques that came after PCA like TSNE and UMAP. The second question that might come across your way is, how does PCA work, or what is the algorithm behind PCA? So the first step is to standardize your data. That is basically ensuring that each feature has a mean of 0 and a standard deviation of 1. And the way to typically do that is you take in your original input matrix, input data matrix, say we call it as X. For each of the feature, you subtract the mean of that particular feature and divide it by the standard deviation, and that will land you at the standardized input data matrix. Let's call that X standardized, right? The second step is to compute the covariance matrix. Now, I'm pretty sure that a lot of you might be aware about what is covariance. And the way to compute the covariance matrix is you take in the above standardized data matrix, you multiply it with the transpose of that particular matrix, and you divide it by n minus 1. And n is basically the number of rows or your number of observations in your original data set. The next step is to perform something called as eigenvalue decomposition, and this is done to compute the eigenvectors and the eigenvalues. And if a corresponding eigenvalue is say lambda and the corresponding eigenvector is say v, then the way that you would typically do that is lambda times v is s times v, and s is the same covariance matrix that we computed above in the second step. And that is how you would calculate the eigenvectors and the corresponding eigenvalues. And what these would represent is the eigenvectors would represent the directions of the maximum variance. And remember, when we are doing PCA, our goal is to find the directions or the principal components which maximize the variance, and the eigenvalues would represent the magnitude of variance in these directions. These eigenvalues would also denote the percentage of variance explained along the corresponding eigenvector. So what I mean by that is, if you have an eigenvector which is called say v1 and the corresponding eigenvalue is say lambda 1, so the percentage of variance explained for v1 could be given as lambda 1 over lambda 1 plus lambda 2 plus so on up till lambda k, assuming that there are k principal components that you have calculated corresponding to your data. And K, like I mentioned, is the dimensionality of the reduced data or the data post applying the principal component analysis. And the next step would be to sort the eigenvalues, say lambda I, and the corresponding eigenvectors, say vi, in the descending order. Select the first k eigenvectors corresponding to the largest k eigenvalues, and these would form your principal component matrix. Let's call that W. And W is typically given as all of these matrices that you have found out, or all of these eigenvectors that you have found out, say v1, v2, so on up till vk. And the last step is basically to transform your original data. You take in your principal component matrix W, you multiply it with the standardized input data matrix, that is X standardized, and you end up with the reduced data, which is after applying the PCA. And like I mentioned, the core idea behind PCA is to project your data into new orthogonal axis, that is what we call principal components, that maximizes the overall variance of the data. And one of the important things to note here is that any two eigenvectors of the covariance matrix are orthogonal to each other. That means that the angle between any two principal components is 90 degree, or in other words, the dot product between any two eigenvectors is going to be 0. Now, the next important question that might be asked to you is, why standardize your data for PCA in the first place? So there are multiple reasons to that. The first reason could be the equal contribution of features. So different features in your data can have different units and scales, and without standardization, features with larger scale will dominate the principal components, and that will not be good, right? So that is the first reason that why you should standardize your data before applying PCA. The second one could be the accurate variance capture. So PCA, like we mentioned, tries to find the direction of maximum variance, and standardizing your data ensures that all the features contribute equally to the variance, allowing PCA to find more meaningful patterns in your data. The third one would be mathematical stability. So standardizing the data helps in obtaining a more stable and accurate covariance matrix, which ensures reliable PCA results. So these are some of the reasons which you might want to mention to the interviewer, because of which you would want to standardize your data before applying PCA. And then the next question could be, what is the significance of eigenvectors and eigenvalues in PCA? So like we mentioned above, eigenvalues indicate the variance captured by each principal component. So the variance explained by a particular principal component, say PC of I, could be given as the corresponding eigenvalue, that is say lambda of I, and divide that by the sum of all the eigenvalues that you have. So this is how you can explain the variance explained by each principal component. And the eigenvalues also helps in determining the number of components that you have to retain. And we will talk about this in one of the subsequent interview questions, but this is how you can use the eigenvalues, and this is the significance that they hold. Talking about eigenvectors, so eigenvectors typically define the directions of principal components in the new feature space. That is pretty evident, and that's what we understood above. And apart from that, it also shows how the original features combine to form the principal components. So each of your principal components which you identify are nothing but a linear combination of your original features. So to understand that, let's take an example. Consider a data set with say 3 features, x1, x2 and x3. The eigenvectors, suppose after performing PCA, come out to be say v1, v2 and v3 with the respective values as shown. And the way you would define principal components is a linear combination of your original features, right? So principal component 1 in this case would be 0.6 times x1 plus 0.7 times x2 plus 0.4 times x3 based on the eigenvector that we can see above in v1, right? And similarly, you can compute PC2 and PC3. And that's how you have the significance of the eigenvectors in your PCA. The next important question that might come across you is how to select the number of principal components to choose, right? That's a very important and a very logical question that might come across. And remember, the goal of PCA is to maximize the amount of variance explained by the principal components. Therefore, what one can do is they can use a cumulative explained variance plot. And the way that would work is, on the x-axis, let's plot the number of principal components to choose. That's what we want. And on the y-axis, let's plot the cumulative variance explained when we choose different number of principal components. And now based on a threshold, you can decide how many number of principal components that you have to choose. So you can identify the number of components needed to reach a desired level of explained variance. So say you want 90% variance to be explained by a principal components. So based on the y-axis and then looking at the x-axis, you can figure out the number of principal components that you might want to select. And that is one of the best ways of choosing how many number of principal components to include in your PCA analysis. Now the next important question on PCA could be, what are some of the limitations of PCA? And this question is basically asked to have an understanding of how in depth you know about PCA and what are some of the drawbacks and where you would not want to use PCA as a data scientist. So the first limitation is the assumption of a linear relationship. So PCA assumes that the principal components are linear combinations of the original features like we discussed above. And if the underlying structure of your data is non-linear, so say for example something like concentric circles or spirals, PCA might not be able to capture the true variance in the data. And that is one of the problematic things that might come across, right? The second sort of limitation for PCA would be it captures the global structure but misses the local structure in your data. So PCA focuses on capturing directions of maximum variance like we discussed above across the entire data set. And this might be a problem because this represents the global structure of your data. However, if there are local relationships and neighborhood structures that are there within your dataset, then PCA might not be the best choice for you. There is another algorithm called TSNE, which can help you capture the local structure of the data and the neighborhood structures. But that would be a topic for another video maybe. But long story short, PCA captures the global structure very well, but misses out on the local structure of your data. The third one is the sensitivity to outliers. So PCA is quite sensitive to outliers because it uses variance as a measure of spread, and outliers can disproportionately affect the direction of your principal components. And also the outliers will have a huge impact on your mu and your sigma square, that is your variance. Therefore, they can impact the calculation of the covariance matrix, and that might indeed result the principal components to be skewed towards the directions where the outliers lie. And therefore, outliers and a sensitivity to outliers is another limitation or drawback of your PCA algorithm. The fourth one is interpretation of principal components. So the principal components that you have are the linear combinations of the original features like we have discussed many times in this video above. And this can make them difficult to interpret, especially when your dataset has many features that are contributing to each of the component. So the interpretation of the principal components might be another limitation or challenge which you might have when you are doing this PCA analysis. The next interview question is, what is a kernel PCA? This is a slightly advanced question and might or might not come, but it's good to know that. So a kernel PCA is an extension of the standardized PCA that allows for a non-linear dimensionality reduction. So remember, we discussed about that linearity is one of the most fundamental assumptions that we have when we are performing PCA. So kernel PCA is simply an extension of that for non-linear structure in your data. And it basically uses kernel functions to map the data into a higher dimensional space where the linear PCA can be applied. The idea is that in this higher dimensional space, the data is linearly separable, and that's where you can apply your standardized PCA or your linear PCA over there. The covariance matrix is also computed in this higher dimensional space, and this is typically achieved using a kernel function. And some examples of a common kernel function could be a polynomial based kernel or a sigmoid based kernel, or one of the most famous and popular kernels is an RBF kernel, that is radial basis function based kernel. And if you know about SVM, so you are right, the idea is derived from the kernel trick that is used in SVM. And there also the idea is same, that you transform your data into a higher dimensional space where it is linearly separable, and there you can apply your linear SVM there. So the idea is derived from a kernel based SVM. Another question could be, what is the time complexity of PCA? So assuming your input data has n rows and d columns or d features, the computation of a covariance matrix, like you can see from this formula, would be order of d squared, because you would have d features or d columns, and you do it across the entire dataset with n rows. Therefore, the time complexity for the computation of covariance matrix would be order of n times d square. And the time complexity for the eigenvalue decomposition, that is the computation of your eigenvectors and eigenvalues, would be order of d cube, assuming you have d features. Therefore, the total time complexity for PCA would be order of n d square plus d cube. So this is another important interview question that might come across you. So these are some of the most important interview questions that we discussed in this particular video that are very important to know. And I have tried to ensure that I try to explain PCA from a very fundamental basis. And if you are preparing for an interview, I believe that this exhaustive list of questions on PCA would help you in your next and upcoming data science interview. So thank you so much for sticking till the end. I hope that this particular video helped you, and it takes a lot of effort to prepare such content and bring it to you. So I would really appreciate if you can like this particular video and subscribe to this channel, because I plan on uploading more such content and helping you land your next data science role in your best company or in your dream company. So this is it for this video then. See you in the next video. Bye bye and take care until then.